Well, in this week, the 11th week, I'll be discussing some techniques of NDT, non-destructive test techniques, which are used in condition monitoring, not in real time, unlike vibration monitoring, but some of the tests which are done in stationary machines to detect the faults. So, the non-destructive tests which are prevalent in the industry for CBM, if I was to list them down, ultrasonics is one of them. Then we have the acoustic emission, eddy current test, dye penetrant test, radiography, as you will see, these are not real time, but they have a lot of engineering applications. To find out the product quality, bearing perhaps eddy current, which could be used to, as you would have seen in the case of journal bearing, to find out the clearances. Okay. Suppose, so today in this lecture we will focus mostly on ultrasonics. Okay. As you know from sound wave, the human frequency audible range is from 20 hertz to 20 kilohertz, and something beyond 20 kilohertz are known as ultrasonics. And so, they are very high frequency waves, and high frequency waves are directional. Okay. So, if I have two materials, okay, with having an impedance Z1 and Z2, so Z1, Z2 are the material impedance. Okay. For example, for air, Z1 is rho times C. Okay. So, speed of sound is dependent on the medium. They may be of a different density, rho 1, rho 2, and C1, C2, speed of sound in the medium. So, what happens if at an interface I have a wave of some incident, okay, this will get reflected. It is because of this impedance Z2. Okay. So, if I consider the reflection coefficient R is nothing but PR by PI. Okay. So, R by rho 1 C1 in this case will be Z2 minus Z1 by Z1 plus Z2. Okay. From wave motion you can find out. So, what happens if materials have different impedances, they will reflect. Now, because these are all ultrasonic waves, this is true for acoustics, audible acoustics as well. If there was a defect in this medium, BM, which has a different impedance Z3, okay, and if I had a system wherein I was, because they are linear, I was scanning along this surface. So, every time the PR would change depending on Z2, but suddenly when it comes here, the reflected wave amplitude would change, because there is a defect. It could be a void, it could be an air gap, it could be some crack. So, these are very helpful when, so ultrasonic waves can penetrate into the material, because they are high frequencies, they have a lot of energies, okay, and then we can use them to penetrate materials. Of course, the power would be very high, but nevertheless we can use them to find out. Of course, the most important thing is that I need to know rho 2 C 2. C is speed of sound in that medium. Okay. So, the characteristics of ultrasonic waves is they are high frequency. Typically, usually waves greater than 1 megahertz are used. So, I can have a ultrasonic generator, which is nothing but a piezoelectric crystal, which is made to oscillate and generate a very high frequency ultrasonic waves. Okay. And speed is different in different materials. For example, in steel, C is 5000 meters per second, and the wave intensity of course would decrease after a certain depth, which is known as the penetration depth. So, if you have a thicker body, we need to have a more powerful ultrasonic wave generator. Now, I will give you an example, a practical application. Say I have a railway wheel set. Now, imagine in this axle a crack has developed. Okay. So, what I could do on the surface, I could have a probe, a UT probe, which is generating waves, and then of course, this is at an impedance Z1, this is an impedance Z2, this has an impedance Z3. So, if I see the reflected wave back, okay, and if I am scanning with maybe this entire length of the axle, I will see a certain intensity of this reflected wave, which I can measure in this ultrasonic, and suddenly I will see at some location that this has decreased. So, I can know even by a go no go basis. So, something is foreign, so because of Z3, I do not know what it is, but something is not abnormal. It has to be uniformly Z2, reflected wave because of Z2, but here this is because of Z3. Okay. Such ultrasonic scans are used to find out internal defects in structures. Suppose you have welded a structure. How good is your weld? Okay. So, in fact, some of the standards which are particularly used in nuclear reactors, nuclear reactor pressure vessel are very important components. They have strict codes for weld certification. They require 100% weld inspection by ultrasonics. Okay. I will just give you an example of the railway axle. So, if there was a defect in the axle, this could be scanned and so on. And today, in fact, the idea is we can have such ultrasonic probes. Suppose you have a platform and then your railway wagon just comes into the platform. So, you can have the where we have a person standing and this is the track. So, we can have cameras with UT probes with an RFID tag. Every axle has an RFID tag. So, you can, when the locomotive or train is coming to the platform and it will pass through this camera UT probe, instantaneously you can have this UT scanning and then say whether it is okay or not okay. If it is not okay, you know the from the RFID, you know the you can identify the location and then have the axle replaced or changed, whatever you need to do. So, these are some of the things which we can think they are no longer science fiction, but they are happening as we speak. So, this wave which I drew as a straight longitudinal wave, depending on the incident wave, I can have different modes of this wave. So, I will explain you here. So, different types of ultrasonic waves, and these are piezoelectric crystals, wherein I can have a longitudinal wave. Herein I produce a shear wave. So, it will come across here and then get reflected, okay, because there is an impedance mismatch. Surface wave, if I change the angle of inclination here, this wave would go on the surface. So, depending on where I want to identify a fault, I can use some of these probes. I will give you an example again. Suppose I have two materials which I have welded. And usually to weld, we will. So, this is my weldment. So, we have made a V groove here, okay, and these are all weldment. So, this is maybe I will okay. So, along the thickness. So, what I could do is I could put an UT probe here. So, what happens? This will get, and then and then this will get reflected. Now, imagine if this, and then I scan it all along. So, wherever there is a defect, the probe would get a different intensity of the reflected wave. So, such surface scans can be done to locate the weld defect. Okay. So, how is this ultrasonic transduction happening? So, this is nothing but a wave generator, usually a piezoelectric crystal, and then we have a wave receiver. So, series of ultrasonic waves with a time delay sequence can also be used to produce a phase array. So, that in one go I can scan the entire surface, and there is something which we will see. So, when I have a piezoelectric crystal, so I will have an incident beam. So, job under inspection, it will get refracted because of the density difference, and then some will get reflected. Okay. I am not interested in this reflected beam, rather I want to see how much of refraction is happening. So, I can have an ultrasonic absorbing material here. So, by this we can understand, and if I move this into the plane of this projection here, throughout the edge of the surface I can know whether any defect has occurred and so on. So, ultrasonic is used to find out internal cracks and voids in any type of material, both metal and non-metal, though for non-metal I will require a high power ultrasonic, and usually for thickness detection. Okay. Imagine on the outside. So, for example, here this is a steel block, and we have artificially cut a slot here, and I am putting this longitudinal probe. By the way, this ultrasound is very similar to the ultrasound people do or to find out baby in the mother's womb. So, we put some sort of an gel, okay, because if this impedance Z1 and this impedance Z2, on this layer we put a couplant gel. This is nothing but a water based compound, so that there is no air between the interface of the probe and the material. So, to remove air, a couplant gel is applied, and here also on this surface we have given a couplant gel. So, what happens? How is it measuring the thickness accurately is like this. So, if this is my material, if I am sending an incident beam, so and this distance is L, this beam is going to get reflected back. So, by knowing the time period between the incident and reflected wave, and knowing C is for steel 5000 meters per second. So, twice L is C times T, okay, T is the time. So, I can find out L as T times C by 2. So, this is known to me, this is what this circuitry would measure, okay, and then I can find out the thickness. Now, this is a demonstration, but in the laboratory we have a machine. Obviously, from the outside we cannot measure its thickness. All you do is put a U2 probe on its surface, and then we can find out. And in this case it is 1.7 mm. Many times in many of the process plants I have seen pipelines, thick pipelines, because of corrosion, the material gets eroded, erosion has occurred, or the other way scale deposits have occurred. So, externally to monitor the quality of the internal thickness of the pipe, I can put an do an UT scanning. You can do it UT scanning. Okay. So, there are many applications of ultrasonics in condition monitoring, be it finding out thickness, finding out cracks, weld defects and so on. So, the scanning procedure, there are names given for it. A scan is a one dimensional scan, B scan is a two dimensional scan or a surface scan, and C scan is a volume scan. But most important is, as I was mentioning, this impedance matching. So, coupling agent is to be used between probe and surface, okay, and that is something one has to keep in mind. Now, recently a new technique has come in ultrasonics, that is the phased array technology, wherein rather than having a long conventional probe, we have this sensing element cut into many elements, and each one of them could be energized to give an ultrasonic wave. So, in a quickly, because as you know, when there is 100% inspection of material quality required, it becomes time consuming to just do a scanning with one UT longitudinal probe. Instead of that, imagine if I have a full surface full of probes. Okay. So, this can be made, and then a mosaic can be done. Phased array is a mosaic of transducers elements in which the timing of the elements excitation can be individual controlled to produce certain desired effects, such as steering the beam or focusing the beam. For example, I could be giving excitation, I could timing it, maybe I will illustrate it in the next diagram. So, some of this phased array beam forming is done. Okay. So, if I give a pulse into this unit, and if I delay and play around with the pulse durations, I can get a circular wavefront, I can get a planar wavefront, I can get a pointed wavefront. Okay. So, this kind of arrangements can be done, and then of course, the reflected signals or the echo signals is dependent on the flaw, and there will be a time delay. So, and by processing this time delay, okay, we can pinpoint the fault. So, this is known as TDOA technique, time difference of arrival. Okay. And then by this we can find out the fault. For example, in large aircraft wings, this is the fuselage. Okay. We can do U2 scanning to find out a defect on the surface of the skin of the aileron, okay, or the flaps, and then we can find out the faults by having such phased array technique. So, you see how this different beam generation and focusing can be done. Elements are pulsed with different time delays. Elements in the array are yellow. Applied to each element is in green. The delay has been given. So, less delay here, and that is why we can focus a beam to this. So, what happens in the sense, because my region of interest is right here, I can focus it by having such phased array. So, they are more powerful than a conventional single longitudinal . And of course, there is a lot of signal processing involved, because the most essential element is this time delay between the incident and the reflected waves. Okay. So, time delay or time difference is the key to finding out the location of the fault. This has been exploited to find out, develop ultrasonic thickness gauges, and this has been exploited to use them to find out weld defects. So, here in a shear wave, the time delay has a slant pattern. So, focusing can be added. I can steer the angle. Okay. So, all these are done through signal processing units, and many commercial such handheld analyzers are available. Okay. So, this can be applied and so on. So, the beam steering can be applied as the capability to modify the refracted angle of the beam generated by the array probe, allows for multiple angle inspection using a single probe. Okay. So, this becomes very easy for the user to do a scanning by ultrasonic. I can do a linear scanning, I can have the elements, but then electronically I can give a signal, so that the elements do not move, but I will move the signal of excitation. So, I just place an electronic mosaic of elements on it, do not move anything here, but move the excitation signal, high frequency, and then do a scanning and so on. Okay, this is an example of the linear scanning, where I am charging them separately. I am not physically moving the transducer, but just exciting them the one by one, the elements of the phased array. So, this is also very, very important. So, a lot of new technologies are being developed, and commercially some of these are available. So, different phased array scans are available. Okay. So, this is a weld defect. So, we can do that and so on. Okay. So, the entire depth of this weldment is scanned. Since I am moving it, this angle is not changing, but as opposed to this. So, we can scan the entire surface, and this is what is essential when we do the weld defect scanning. And so, I can identify if there is a reflection here, I can identify where the spot is. So, such arrangements are there. Okay. So, why phased array? High speed electronic scanning without moving parts, improved inspection capabilities through software control, inspection with multiple angles with single and electronically controlled, and greater flexibility. Okay. So, this is a view of a typical phased array equipment which we have in our laboratory, and some of these I will show you maybe in the last slide of our lectures here. Okay. Thank you.